Okay, so we're going to connect these ideas of intermolecular forces and how it affects the overall properties. So when we're looking at just our compounds, the state of a substance depends on the strength of the attractive forces. The strength of the attractive forces between its particles. Solids have the greatest forces of attraction. Liquids have the next greatest. And gases have very few, if any, intermolecular attractions because they're just bouncing around too much. They don't come into contact with each other as much. So when we think about our melting and boiling point, the melting and boiling points are indicators of the strength of attractions within or between molecules. So it kind of tells us how strong they will be. When metals melt or boil, metallic bonds must be broken. And I'm going to go through metallic bonds in more detail next week, too. So it's like those molecules are holding together, and boiling point and melting point tells us how much energy it takes to split them apart and break those intermolecular bonds. Okay? So it's an indication of the energy needed to break it. Okay? The energy needed to break it. Oh, you're doing 5 minutes?
Well, I tried to, but I can't.
Yeah, I know. When ionic compounds melt or boil, the ionic bonds must be broken. So that ion-to-ion attraction that's creating that overall ionic bond needs to be broken. When molecular compounds melt or boil, okay, so now this is our intermolecular forces. When molecular compounds melt or boil, only intermolecular forces will be broken. This is really important, okay? The covalent bonds stay together. Because remember on our chart, our scale of forces, covalent are so strong that they won't break apart. So covalent bonds do not break when melting and boiling. So it's all of the bonds between the molecules, okay, that would break, like the hydrogen bonding, the London dispersion, and the dipole-dipole. Because these forces are much weaker, therefore it takes a lot less energy to separate the molecules. As you increase the number of intermolecular forces, the melting and boiling point increases. So we think about this as being like energy needed to break intermolecular bonds. Okay, so as we increase our intermolecular bonds, the temperature needed, which is energy, to break it will increase. Okay? So as intermolecular forces increase, what will also increase? Melting and boiling point. As boiling point and melting point increases, what else increases? Intermolecular forces, okay? Stronger forces, more energy to break them. Got it? Okay? Very important. Okay? All right. So, the greater the intermolecular bond, so this is our main conclusion, the greater the intermolecular bond strength, bond strength, between molecules of a compound, the higher the melting and boiling point of that compound. Why? Because, what did I just say? It takes more energy to break those bonds. Yeah, write that in. Because that melting and that boiling point is really energy. Representation of that energy needed to break the bonds. So this is kind of the premise of, we're going to apply this now, and we're going to analyze boiling point and melting point of different compounds, and we're going to look at the intermolecular forces that are happening in those compounds and kind of analyze it. So using your scale of forces, you can order compounds based on their relative boiling points from highest to lowest. So say a compound has network covalent bonds, it's going to have a really high melting point, okay? Basically, you won't be able to melt it. Then our ionic compounds would be the next one, right? Your scale of forces, remember that? Remember your scale from yesterday? Yeah? Pull out your scale from yesterday's notes to look at. It was on the very back. Yeah. Yeah, exactly. Good. So our covalent networking was the highest than our ionic, right? Oh, okay. And then depending, okay, so, because in between here and here was our covalent bond, right? But the covalent bonds don't break, okay? So any molecular compounds, depending on what intermolecular forces they have, so say you have a molecular compound that has hydrogen bonding, dipole-dipole, and London dispersion. It's going to be strong, so it's going to have a higher boiling point than a molecular compound with only dipole-dipole and London dispersion. Okay? So, now look at your assignment. Let's look at this a little bit together. So I'll give you some hints. So read through just the beginning of your assignment there, and then we will. Okay, so here, this is our first kind of page. Okay, now I don't know if I printed this before or after, but this, oh yeah, I did, okay. So this is the number of electrons of each of these central atoms. So look at, this is just a table to summarize certain things. So here where it says group 14, that's referring to this column here, group 14, okay? And then we have our group 15, 16, 17. So we're going to kind of analyze and look at the boiling point within those groups. And it's really cool actually to see some of these patterns. So how many electrons in the central atom of this one? This is CH4, so the central atom is carbon. How many electrons does it have? Pull out your periodic table. 6.
Yeah.
Yeah, okay. So not counting the valence electrons that it attached to. Okay? So just to start with, how many electrons? So it has 6. Okay. Silicon, how many electrons does it have? 14. Okay. Germanium, 32, and tin. 50, right? That's 10? Yeah, we just go down the group. Okay, so now let's think about this for a second. It starts off as negative 162, goes to 112, negative 90, negative 50. So as I go through this one group, my boiling point is increasing, right? It's getting, it takes more energy, okay, to break the intermolecular bonds. Do you see that? Why? What is changing in these molecules? They all have the same attachments, so it's the central atom that is changing, right? What intermolecular forces do these have? What does CH4 have? Is it dipole-dipole? It's a tetrahedral, and it has H, H, H. So a tetrahedral with all the same atoms around it, is it polar? Is this polar?
No.
No. So does it have dipole-dipole? Oh, okay. Dipole-dipole, you only have dipole-dipole if it's polar. Right? Yeah, okay, so no. So what can it only has London dispersion. So beside each of these, I actually kind of like to write down which things it has. So what about silicon tetrahydride? Does it have hydrogen bonding? No. Hydrogen bonding only happens when the hydrogen is attached to either N, O, or F. It's the only ones, because they're the only really electronegative atoms that have at least one lone pair. So does it have hydrogen bonding? Nope. Does it have dipole-dipole? Nope, because it's not polar. Does it have London dispersion? Yes. Next one. Does it have hydrogen bonding? No. Dipole-dipole? No. London dispersion? Yes. Next one. Only London dispersion. So, why is the boiling point increasing if they each only have London dispersion? Ha. There's more electrons. Okay? In our notes yesterday, it said London dispersion forces increase when there are more electrons. More electrons, stronger London dispersion, so we have an increase in boiling point. Okay? So I'm actually giving you the answers to some of your questions that will be coming up here, okay, so that you kind of can process through it. Let's do the next group together because it's a little bit harder, okay? So, let's see what time. I might just,